Welcome. In this video, we'll explore the powerful world of C++ templates and the standard template library or STL. Templates are a cornerstone of generic programming in C++, allowing us to write flexible, reusable code that can work with any data type. Whether you're building a simple array or a complex data structure, templates help you avoid code duplication and make your programs more efficient. Let's start by understanding what templates are and why they're so essential in modern C++ development. Templates in C++ allow us to create a family of classes or functions that can operate on different data types. Instead of writing separate code for each type, you write one template and let the compiler generate the specific code as needed. This not only saves time but also reduces errors and makes your codebase easier to maintain. Templates can have type parameters and even non-type parameters like the size of an array. This flexibility is what makes templates such a powerful feature in C++. Unique aspect of C++ templates is the ability to use non-type template arguments. For example, you can specify the size of an array as a template parameter. This means you can create classes or functions that are not only generic in type but also in value. When you instantiate a template with a non-type argument, like an integer, the compiler generates code tailored to that specific value. This is especially useful for creating fixed-size containers or optimizing performance. Templates offer several advantages. They eliminate code duplication, making it easier to manage and update your code. With templates, you can write a single function or class that works with any data type, reducing the risk of errors. Templates also support multiple parameters, allowing for even more flexibility. Plus, template functions can be overloaded, giving you the ability to handle different scenarios with ease. All these features make templates a must-have tool for any C++ programmer. Now that we understand templates, let's dive into the standard template library or STL. The STL is a collection of template classes and functions that provide common data structures and algorithms. It includes containers like vectors, lists, and stacks, as well as algorithms for sorting, searching, and more. The STL is designed to be flexible and efficient, making it a vital part of modern C++ programming. To use STL effectively, a solid grasp of templates is essential. STL is built around four main components: algorithms, containers, iterators, and function objects. Algorithms are functions that operate on containers, performing tasks like sorting and searching. Containers are data structures that store objects, such as vectors and lists. Iterators provide a way to traverse containers, and function objects allow you to customize algorithm behavior. By combining these components, you can build powerful and efficient C++ programs. STL algorithms are a set of functions designed to work with containers. They include operations like sorting, searching, partitioning, and numeric computations. The algorithms are defined in the algorithm header and are designed to be generic, working with any container that supports iterators. This means you can use the same sorting function for a vector, a list, or any other compatible container, making your code more reusable and consistent. Containers are the backbone of the STL. They store and organize data in various ways depending on your needs. There are several types of containers: sequence containers like vector and list, associative containers like set and map, and unordered containers like unordered map. Each container type offers different performance characteristics and use cases. Understanding the strengths of each container helps you choose the right one for your application. Iterators are objects that allow you to traverse the elements of a container. They act like pointers, providing access to container elements and enabling algorithms to work with different container types. There are several kinds of iterators, including forward, reverse, and constant iterators. By mastering iterators, you can write code that is both generic and efficient, seamlessly moving through any STL container. Sorting is one of the most common operations in programming. The STL provides a built-in sort function that can arrange elements in ascending or descending order. By default, sort uses a hybrid algorithm called intro sort, which combines quicksort, heap sort, and insertion sort for optimal performance. You can sort any container that supports random access iterators, such as arrays or vectors, with just a single line of code. Sort function in STL sorts elements in the range start-end. You provide the starting and ending addresses, and the function arranges the elements in ascending order by default. Internally, it uses intro sort, which starts with quicksort, switches to heap sort if needed, and finishes with insertion sort for small arrays. This ensures fast and reliable sorting in most scenarios. Let's look at a simple example. Suppose you have an array of integers, 158967342. Before sorting, the array is unordered. By calling sort a plus a size, where a size is the number of elements, the array becomes sorted in ascending order, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This demonstrates how easy it is to sort data using STL. If you want to sort in descending order, STL sort function allows you to pass a third parameter. By using greater int, you can arrange the elements from largest to smallest. For example, sort r plus n greater int will sort the array in descending order, giving you 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. This flexibility makes STL sorting extremely versatile. Binary search is a fast searching algorithm that works on sorted arrays. The STL provides a binary search function that returns true if the element is found and false otherwise. It works by repeatedly dividing the array in half and comparing the middle element to the target. This divide and conquer approach makes binary search much faster than linear search, especially for large datasets. Consider an array 158967342. To search for a value, first sort the array, then call binary search a plus 10 value. If the value exists, the function returns true. For example, searching for 2 returns true while searching for 10 returns false. This shows how STL makes searching both simple and efficient. Sequence containers in STL include vector, list, deck, and array. These containers store elements in a linear sequence, making them ideal for situations where order matters. Vectors are dynamic arrays, lists are linked lists, decks support fast insertion at both ends, and arrays are fixed size. Choosing the right sequence container depends on your specific needs for performance and memory usage. Container adapters provide a different interface for sequential containers. The main adapters are queue, priority queue, and stack. These adapters use underlying containers like vector or deck, but restrict access to provide specific behaviors, such as FIFO for queues and LIFO for stacks. This abstraction makes it easier to implement common data structures without reinventing the wheel. Associative containers, such as set, multiset, map, and multimap, store elements in sorted order and allow fast searching, insertion, and deletion. These containers use tree-based structures internally, providing O log n complexity for most operations. They are ideal for scenarios where you need to maintain a sorted collection or quickly look up values by key. Unordered associative containers introduced in C++11 include unordered set, unordered multiset, unordered map, and unordered multimap. These containers use hash tables for storage, providing average constant time complexity for insertion and lookup. They are perfect when you need fast access without caring about the order of elements. Vectors are dynamic arrays that automatically resize as elements are added or removed. They store elements in contiguous memory, allowing fast random access and efficient traversal. Inserting or deleting elements at the end is fast, but operations at the beginning or middle are slower. Vectors are ideal when you need a resizable array with efficient access. To use vectors, include the vector header. You can declare a vector with vector object type vector name. Initialization can be done by pushing values one by one using pushback, passing an array to the constructor, or copying from another vector. This flexibility makes vectors easy to use in a variety of situations. Vectors support a range of iterators for traversing elements. Begin and end provide forward iteration, while rbegin and rend allow reverse iteration. Constant iterators like cbegin and crend ensure elements aren't modified. Iterators make it easy to loop through vectors and apply STL algorithms. See iterators in action. By looping from G1 begin to G1 end, you can print all elements in a vector. Using rbegin and rend, you can print elements in reverse order. Constant iterators like cbegin and crend ensure you don't accidentally modify the vector while traversing. This versatility is one reason vectors are so popular in C++. Vectors provide several functions to manage capacity. Size returns the number of elements, capacity shows the allocated storage, and max size gives the maximum possible elements. Resize n changes the vector size, empty checks if it's empty, and shrink to fit reduces capacity to fit the size. These functions help you control memory usage and performance. Suppose you have a vector with 5 elements. Calling size returns 5, while capacity might be higher due to internal allocation. After resizing to 4, size becomes 4, empty checks if the vector is empty, and shrink to fit reduces unused capacity. These tools let you optimize your vector's memory footprint. Vectors offer multiple ways to access elements. Use the reference operator G or @G to get elements at a specific position. Front returns the first element, back returns the last, and data gives a pointer to the underlying array. These access methods make vectors both powerful and convenient. For example, if you have a vector with values 10, 20, 30, 100, G1 2 returns 30, G1 at 4 returns 50, front gives 10, and back gives 100. Using data, you can get a pointer to the first element, which is useful for interoperability with C-style arrays. Vectors support a range of modifiers for managing elements. Assign replaces all elements, pushback adds to the end, and popback removes from the end. Insert and erase let you add or remove elements at specific positions. Swap exchanges contents with another vector. Clear removes all elements and in place or in place back construct elements in place. These modifiers give you full control over your vector's content. See modifiers in action. Assign fills a vector with 5 tens, pushback 15 adds 15 to the end, and popback removes it. Insert can add 5 at the beginning, and erase removes the first element. In place and in place back construct elements directly, while swap exchanges contents with another vector. Clear empties the vector, resetting its size to 0. Vectors are best when you need a dynamic array with frequent changes in size. They're ideal if the number of elements is unknown or if you need to copy data easily. Compared to arrays, vectors offer more flexibility and built-in functions, making them a go-to choice for many C++ developers. Lists in STL are sequence containers that allow non-contiguous memory allocation. They are typically implemented as doubly linked lists, making insertion and deletion fast once a position is found. However, traversal is slower compared to vectors. Lists are perfect for scenarios where you need frequent insertions and deletions at arbitrary positions. Let's look at a list example. You can create 2 lists and fill them using pushback and pushfront. Functions like front, back, pop front, and pop back let you access and modify elements at both ends. Reverse reverses the list, and sort arranges elements in order. Lists are versatile for managing ordered data with frequent modifications. Let's support a wide range of functions: insert, pushback, push front, pop back, pop front, empty, size, max size, front, back, swap, reverse, sort, merge, splice, unique, resize, assign, in place back, and in place front. These functions make lists highly adaptable for various use cases. Stacks are container adapters that follow the last in first out LIFO principle. You add elements to the top and remove them from the top. Stacks are built on top of other containers like vector or deck, providing a simple interface for stack operations. They're perfect for scenarios like undo functionality or parsing expressions. Stacks provide several key functions. Empty checks if the stack is empty. Size returns the number of elements. Top gives access to the top element. Push adds an element to the top, and pop removes the top element. All these operations are fast with constant time complexity. Imagine a stack where you push values 21, 22, 24, and 25. After popping the top two elements, you're left with 22 and 21. Using a while loop and empty, you can print and remove all elements from the stack. This demonstrates how stacks manage data in a LIFO manner, making them useful for many algorithmic problems. Queues are container adapters that follow the first in first out FIFO principle. Elements are added at the rear and removed from the front. Queues are built on containers like deck or list, providing a straightforward interface for queue operations. They're ideal for scheduling tasks or managing resources in order. Queues offer several functions. Empty checks if the queue is empty. Size returns the number of elements. Front accesses the first element. Back accesses the last. Push adds to the rear. Pop removes from the front. In place inserts at the rear, and swap exchanges contents with another queue. These functions make queues easy to use for a variety of applications. Let's see a queue in action. By pushing values 10, 20, and 30, you create a queue. Front returns 10, back returns 30, and pop removes the front element. After popping, the queue contains 20 and 30. This illustrates how queues manage data in a FIFO order, making them suitable for many real-world scenarios. So many containers available in STL. Choosing the right one depends on your needs. Use vectors for dynamic arrays, lists for frequent insertions and deletions, stacks for LIFO operations, and queues for FIFO operations. Associative containers are best for sorted data and fast lookups, while unordered containers excel at fast, unordered access. Understanding each container's strengths helps you write efficient, maintainable code. STL is widely used in real-world C++ programming. Its containers and algorithms save time, reduce bugs, and make code more readable. By mastering STL, you can tackle complex problems with simple, elegant solutions. Whether you're sorting data, managing collections, or implementing algorithms, STL provides the tools you need. Here are some tips for using STL effectively. Always choose the container that best fits your needs. Take advantage of iterators and algorithms to write generic code. Remember to sort containers before using binary search. Use in place and in place back for efficient element construction. And finally, don't be afraid to explore the full range of STL features to make your programs more robust and efficient. Recap: the STL offers a comprehensive set of containers, algorithms, and iterators for efficient C++ programming. Templates make it possible to write generic code that works with any data type. By understanding and using STL, you can write code that is faster, safer, and easier to maintain. The STL is truly a game changer for C++ developers. If you want to learn more about STL and templates, check out the official C++ documentation and online tutorials. Practice by implementing different containers and algorithms in your own projects. The more you use STL, the more comfortable and productive you'll become as a C++ programmer. Thanks for watching. We've covered the essentials of C++ templates and the standard template library, including containers, algorithms, and iterators. By mastering these tools, you can write powerful, efficient, and maintainable C++ code. Keep practicing, explore more STL features, and take your programming skills to the next level.